Hello everyone and welcome to my first video. Now today I'm going to be showing you a really neat little trick for finding eigenvalues of a 2x2 matrix. Now I really want to emphasize this because it's very important. This only works in the 2x2 case, and I'll just try and quickly show you why that is. So the way we actually find this formula is as follows. So in this 2x2 matrix we have something that is called the trace, and that is defined as the sum of diagonal elements, right? So more concretely, in this case, that's going to be A plus D. All right, so I'll just write that out. We have A plus D is equal to the trace, and we'll call this matrix A. So we're going to say that that's the trace of A is the sum of A plus D. Now, an interesting property of any square matrix actually is that the trace of the matrix is the same thing as the sum of the eigenvalues. So you can see we have A plus D is equal to lambda 1 plus lambda 2. And then the next property we have is that the determinant of this matrix is the product of the eigenvalues. So writing that out again, we have that AD minus BC is going to be equal to, which one is it? Yes, it's going to be equal to lambda 1 times lambda 2, right? And now I guess just to simplify some things, we use these letters, right? You might be wondering up here, what is this formula I've written? We say that M is equal to the trace of A divided by 2. Another really nice way you can think about this is it's the average of these two elements, right? That's the quickest way to think about it, And then we have that the product, P, is equal to the determinant of A. Now both these things are relatively easy to find, and that's why this formula is so much quicker than the normal determinant of A minus lambda I method. So that's essentially it, right? Once we have these things, we can solve this, and because we have the same number of equations as we have unknowns, this works for 2x2. Unfortunately, it doesn't work for 3x3, but that's okay. So essentially, right, once we find this over here, we find this M is equal to the trace of A divided by 2, and then P is equal to determinant of A, we simply plug it in to this formula that I've written up here, and that is M plus or minus square root of M squared minus P. Now I'll be honest, the idea for this video came from a 3 blue 1 brown video, which I'll try and link in the description below. They've done a great job explaining some of the theory behind it, as well as a catchy little tune to remember it by. But I'm sure you guys are interested in seeing an example, so I'll go right into that now. So let's look at this matrix we have below. I'll actually just shift this a little bit up so everything stays in focus. Okay, first thing, right, we want to find M, and in this case that's going to be the average of the diagonal elements. Here the diagonal elements are 3 and 3, so the average of those is just 3. And then the P, which is also the determinant, is going to be 3 times 3, 9, minus 1 times 1, which is 8. And then to find our two eigenvalues, we will say, I'll just say lambda generally, is equal to 3 plus or minus square root. We have M squared, which is 9 minus 8. And then we can simplify that. I'll just put it down here to say that lambda is equal to 3 plus minus 1, which is equal to either 2 or 4. Now you can absolutely go ahead and use the determinant of A minus lambda I to verify that this is indeed true. But I'm sure you can kind of see that this is a really fast method, and it's super efficient, especially when you're doing something like solving differential equations that require you to know these, find the eigenvalues, eigenvectors of a 2x2 system. So this is a really cool and efficient method. Let's try this other one real quick. Let me actually give you an option to pause the video now and try this one on your own before I go ahead and give the solution. Okay, so the M, right, in this case, our average is going to be M equal to negative 2, and then the P here, right, 0 times negative 4 is just 0, so then we're just subtracting 12. So in this case, our P is just negative 12. Like before, we're going to say that lambda is equal to M plus or minus square root of M squared, and this time we have minus negative 12, which is the same thing as adding 12, right? So then that radical will simplify to 16, and then the square root of 16, hopefully you remember, is 4. So then we can say down here that lambda is equal to negative 2 plus minus 4, which then is equal to either negative 6 or 2. So this is really nice, and it's super fantastic because it covers every single 2x2 matrix that could possibly exist, right? Let's say you have repeated eigenvalues. In that case, right, maybe you can predict that this determinant will just be 0. Or not the determinant, sorry. This square root will just be 0. So then m plus or minus 0 is just m. So that's a repeated roots. And if your m squared minus p is if negative, then you will get the imaginary eigenvalues. Now, understandably, not everyone is interested in that, but this is a very, very efficient trick for finding the eigenvalues of a 2x2 matrix. Anyways, I hope you guys found this video helpful. I had a lot of fun making it. So yeah, that's about it. Thanks.